Modern civilization requires an immense, unwavering supply of carbon-free electricity to power everything from manufacturing hubs to AI data centers. While renewables like wind and solar are expanding, they still require a high-density, reliable baseload partner that can run 24/7 regardless of the weather. Nuclear energy is the only proven technology that fits that bill, but the industry has spent decades trapped in a cycle of clunky, custom-built megaprojects. This data shows how first-of-a-kind reactors routinely suffer from ballooning capital costs and multi-year delays. When every reactor is a massive, bespoke engineering experiment, the financial risk becomes too high for almost any private investor to touch. The proposed solution is to shift the scale from mega to micro. By mass-producing small, standardized reactor units in a factory setting, the industry can finally leverage the same economies of scale that made the automotive and aviation sectors profitable. But modular manufacturing doesn't solve the bureaucratic friction. Even a small reactor must undergo a grueling, years-long approval process to prove its design is safe, creating a regulatory bottleneck that stops most micro-startups before they can even break ground. Without a radical shortcut to accelerate design and safety validation, the vision of a modular nuclear future will remain grounded. The Idaho National Laboratory is being transformed into a centralized testing ground designed to find that shortcut by merging advanced software with nuclear physics. This is the Genesis mission, a new national-level initiative to integrate artificial intelligence into the very foundation of nuclear engineering. Through Project Prometheus, NVIDIA is providing the processing power necessary to turn massive libraries of historical reactor data into predictive digital blueprints. These digital twins allow engineers to simulate thousands of virtual scenarios, testing extreme heat or structural stress long before physical parts are manufactured. By solving flaws in simulation, this compresses years of trial and error into a single, verified design. But these simulations can only go so far. For a design to be licensed for the real world, the AI's virtual data must be anchored to physical hardware. That anchor is the MARVEL microreactor, a first-of-its-kind hardware testbed inside INL's transient reactor test facility. MARVEL is a compact 85-kilowatt thermal system using a liquid sodium-potassium coolant. Its internal architecture relies on passive safety features. Even without human intervention or external power, the physical properties of the coolant naturally prevent the core from overheating. Generating real-world data from a physical system like MARVEL is the only way to satisfy federal regulators that these passive safety designs function as predicted. This isn't just a future goal. Fuel fabrication is already underway, moving the project from a research model to an active reactor. MARVEL provides the empirical proof needed to transform AI-driven simulations into a licensed commercial energy solution. The operational data from MARVEL is being mapped directly to the Nuclear Regulatory Commission's upcoming 10 CFR Part 53 framework, a new pathway designed specifically for advanced reactor technologies. By feeding high-fidelity physical data into a streamlined regulatory structure, INL is creating a fast pass for microreactor deployment. The nuclear industry has been stalled for decades by high costs and rigid timelines, but in 2026, the first physical results of this new approach are emerging in Idaho. The Genesis mission is proving that digital twins can accelerate the path from a designer's screen to a working reactor in months rather than years. With the MARVEL microreactor providing the physical validation, the industry is finally moving toward a mass-produced nuclear battery. The data-rich environment of the Genesis mission and the physical hardware of MARVEL enable the deployment of decentralized, clean energy at a global scale.